When ChatGPT writes a sentence, it's doing one thing at each step, picking the most likely next word from a list of 100,000 possibilities. But how does a neural network, which only outputs raw numbers, produce a probability distribution? And how does it learn to make those probabilities better? Two functions, Softmax and Cross-Entropy. They're the bridge between neural network outputs and human-readable predictions. And they're elegant pieces of mathematics. The final layer of a neural network outputs a vector of raw scores, called Logits. For a language model with 100,000 tokens in its vocabulary, that's 100,000 numbers. These Logits can be anything, positive, negative, large, small, they're not probabilities. Probabilities must be between 0 and 1 and must sum to 1. We need a function that takes any vector of real numbers and converts it into a valid probability distribution. That function is softmax. Softmax of zi equals e to the zi divided by the sum of e to the zj for all j. Let's unpack this. First, we exponentiate each logit, e to the power of each number. This makes everything positive. Then we divide by the sum of all the exponentials. This forces everything to sum to 1. Let's compute an example. Logits 2,1 and 0.1. The exponentials e squared is about 7.39, e to the 1 is 2.72, e to the 0. 1 is 1.11. The sum is 11.22. So the probabilities are 7.39 over 11.22 equals 0.66, then 0.24, then 0.10. The largest logit gets the highest probability, but every option gets some probability. Nothing is exactly 0. You might ask, why use exponentials? Why not just divide each number by the sum? Because some logits are negative and negative numbers can't be probabilities. The exponential solves this. E to any power is always positive. But the exponential does something more. It amplifies differences. The gap between logits 2 and 1 is just 1, but the gap between their exponentials is 7.39 versus 2.72, a ratio of 2.7. The exponential makes the model more decisive. Big logits dominate. This is controlled by a parameter called temperature. Divide the logits by temperature T before softmax. Low temperature, say 0.1, makes the distribution very sharp. One word gets nearly all the probability. High temperature, say 2, makes it flatter. All words get similar probability. Temperature 1 is the default. Softmax appears twice in a transformer, first inside the attention mechanism. Remember from episode 7, the attention scores, the dot products of queries and keys, are raw numbers. Softmax converts them into attention weights that sum to 1. Each word distributes 100% of its attention across all other words. Second, at the very end, the final layer produces logits, 1 per token in the vocabulary. Softmax converts these into the probability of each possible next token. When you see GPT choosing a word, it's sampling from this softmax distribution. Now we have probabilities, but during training we need to measure how good those probabilities are. Enter cross-entropy, which we saw in episode 5 for binary classification. For multi-class, the formula is L equals minus the sum over all classes of yi times log of pi. Since the true label is 1 hot, say the correct next word is mat at position 4237, this simplifies to L equals minus log of p 4237, just the negative log of the probability the model assigned to the correct answer. If the model gave 90% to the right word, loss is minus log of 0.9, which is 0.105, low loss. If it gave 1%, loss is minus log of 0.01, which is 4.6, huge loss. If it gave essentially 0, the loss approaches infinity. Here's something elegant. When you compute the gradient of cross-entropy loss after softmax, the math simplifies beautifully. The gradient with respect to the logits is simply pi minus yi, the predicted probability minus the true label. For the correct class, the gradient is p minus 1, pushing the probability up toward 1. For all wrong classes, the gradient is just p, pushing their probabilities down toward 0. No exponentials in the gradient, no logarithms, just a subtraction. This is why softmax and cross-entropy are always used together. Their gradients are clean, stable, and fast to compute. Deep learning frameworks compute them as a single fused operation for numerical stability. One practical detail that every engineer knows. Computing softmax naively is numerically dangerous. If a logit is 1000, e to the 1000 is a number with 434 digits. It overflows to infinity. The fix is simple and clever. Subtract the maximum logit from all logits before exponentiating. This doesn't change the result. The softmax is shift invariant. But it prevents overflow because the largest exponent is now e to the 0, which is 1. Similarly, computing log of softmax directly causes underflow. The log-sum-exp trick computes log softmax in a numerically stable way. This is why you should always use the library function. Never implement softmax yourself. When researchers evaluate language models, they report perplexity, not raw loss. Perplexity is simply 2 to the power of the cross-entropy loss, or equivalently, e to the power of the loss if using natural log. A perplexity of 20 means, on average, the model is as uncertain as if it were choosing uniformly between 20 options. Lower perplexity is better. A perplexity of 1 would mean the model predicts every next word perfectly. GPT-3 achieved a perplexity around 20 on standard benchmarks. Modern models are lower. When you read that a model has lower perplexity, now you know exactly what that means. Its softmax probabilities are closer to the true distribution. One episode left. Next time we close the series with tokenization and probability. How AI actually reads text, why it doesn't see words the way we do, and how the entire system comes together into one coherent prediction machine. Subscribe for the grand finale. See you in the next one.